In today's lesson, we are going to be looking at special triangles. So this is our first lesson in the trigonometry unit, and we are going to be looking at some specific scenarios first before we start kind of reviewing some of the concepts that we've looked at before. But first, we're going to look at, again, a little bit of review. Right? Remember, we have three primary trigonometric ratios for right angle triangles, and those are sine, cosine, and tangent. Right, so remember, when you have your right angle triangle, you want to make sure that you have your reference angle. In this case, we labeled it with theta, which is just this Greek letter here, which just refers to our reference angle. And we need this reference angle because it's going to help us label the sides that we're going to use for our three trig ratios. Right, so we have our opposite, which is across from our angle, or our reference angle. We have our hypotenuse, which is across from the 90-degree angle, or you could think of it as the longest side. And then you have the adjacent, which is beside our angle, right, our reference angle. Or once we find the opposite in hypotenuse, it's the only other angle left. The three trig ratios, sine, cos, and tan. Right, so sine of an angle is equal to the opposite side divided by the hypotenuse. So these are referring to the lengths, right, the lengths of each side. So this opposite side divided by the hypotenuse. Cosine is adjacent over hypotenuse, and tan is opposite over adjacent. Now, if we know that a specific right angle triangle has an angle of theta, or just some angle, all other right angle triangles with an angle that is the same are considered similar. Right? So back in grade 10, you probably learned about similar triangles. Right? So if two triangles share the same angle, and they're both right angle triangles, and that means they're similar triangles, and therefore they're going to have equivalent ratios for all the corresponding sides. Right? So the size may be a factor larger, but it's going to be the same across the board. So again, some acronyms, right? SOHCAHTOA, right? We can use that as kind of like the acronym to help us remember our three right angle trig ratios, right? So SOH, sine is equal to opposite over hypotenuse, CAH, adjacent over hypotenuse, and TOA, opposite over adjacent. Right? So those are the three trig ratios or right angle trig ratios that we should be familiar with already. Right, so let's kind of use that to help us find the missing side. Right, so I have my angle. I want to then label the sides that I'm given. Right, I do have my opposite here, and I have my hypotenuse. So because I'm dealing with O and H, I'm going to be using sine. So sine theta equals the opposite over the hypotenuse. Sine of 30 is equal to 1 over x. In this case, I can just switch. Or bring the x up and then bring the sine 30 down. Either way, x is equal to 1 over sine 30. And this I can calculate, and I get that x is equal to 2. So that is my missing side. If I want to find an angle, right, similar idea, I still need to label my sides. So I have my reference angle, I have the hypotenuse, the longest side across from 90 degrees, and I have the adjacent. So this tells me, right, that I should, going back to my acronyms, that I should be using cosine. So it's cosine of an angle is equal to adjacent over hypotenuse. Cosine of an angle is equal to root 2 over 2. And in order to get theta by itself, I need to move the cosine over or cancel the cosine out. And we do that by using what we call the inverse. So the inverse of cosine, or cosine -1. Keep in mind that this is just a function, right? It's not cosine to the power of -1. It's the inverse of cosine. So the inverse of cosine of root 2 over 2. So it's just a button on your calculator that you're going to find. It's probably going to be associated with the actual cosine button. So you're probably going to have to do something like second button or shift and then plus the cosine button, right, to get it, right? If you look above your cosine button, there's probably cosine -1 in a different color. That's what we're referring to here. So I just plug that in, cosine -1 in brackets, and then √2 divided by 2, and I get my angle, which is equal to 45 degrees. So that means that reference angle is 45 degrees. And so that was a little bit of a review of kind of the right angle trig that you've looked at before. We're going to focus specifically now on special triangles. And we're going to look at two types of right angle triangles. One is going to be an isosceles triangle, which means two angles are the same or two sides are the same. And it's going to be a 45 degree, 45 degree, 90 degree triangle. We're then going to look at an equilateral triangle that's split in half. So the angles that we're dealing with are 30, 60, and 90. Now the key reason we're looking at these two types of triangles is because we get exact values. Right, so we get exact values for the three primary trig ratios using these special triangles, and we can do it without a calculator and with no decimals. Right, so we're getting exact values, and it's always going to be like that for these two scenarios. So let's look at the first one. Right, 45 degree, 45 degree, 90 degree. Right, so I have a 45 degree angle here. That means because these two sides are the same, that means this angle also has to be 45 degrees. Now, let's give it a ratio, or let's label these sides. Let's say it's a length of 1 and a length of 1. We're going to do the simplest isosceles triangle that we could deal with. I'm going to pick an angle to work with. I'm going to say this one here is my theta. So if that's theta, then this is the opposite. This is the hypotenuse. Oh, not the hypotenuse. The opposite and the adjacent. This is the hypotenuse, but I don't have a side for it yet, right? I'm missing a side. However, because it is a right angle triangle, I can use the sum of squares, or you might know it as the Pythagorean theorem. So the a squared plus b squared equals c squared. 1 squared plus 1 squared equals c squared. 1 squared is 1 plus 1 squared, which is 1 again, so I get 2 equals c squared. And then to get c by itself, I take the square root of both sides. So the square root of 2 equals c. I'm going to leave it as the square root of 2. And that is going to be my side length, or my hypotenuse. So now that I know that, I can go through and come up with my three primary trig ratios. Sine of 45, because that's my reference angle, is equal to the opposite over hypotenuse, so 1 over √2. Cosine 45, adjacent over hypotenuse, so 1 over √2. And then tan of 45, opposite over adjacent, is 1 over 1, or just 1. So those are the three primary trig ratios for this special triangle, or this particular special triangle. And those are the exact values. There's no decimals or no, it's not rounded, or it's not like a long repeating decimal or a never ending decimal. These are the exact values. With our equilateral triangle, the 30, 60, 90, it is going to be an equilateral triangle split into two, right? So if it's, let's say we have a side length of 2 for the hypotenuse, 2, 2, and 2. Right, so just again, kind of dealing with a simple version. If this is 90 degrees and it's equilateral, that means each corner is 60 degrees. Let me keep it consistent. And if it's an equilateral, then that means this this altitude, this height, perfectly bisects this upper angle. So that means it's 30 for each half, or it splits it into 2. And because I'm dealing with an equilateral triangle, this line also will then come down and bisect, so that each one is, or each part, or each triangle has a base of 1. Now I am missing this height, right? But for this height, I can again use the Pythagorean theorem, or the sum of squares. B squared equals c squared minus a squared. B squared equals 2 squared minus 1 squared. B squared equals 4 minus 1, which is 3. And I get b equals root 3. So that is the height of this equilateral triangle. Now that I have these, I can go through and come up with my primary trig ratios, and I'm going to have it for two different versions. One for dealing with a reference angle of 60, and one dealing with a reference angle of 30. So let's start with 60 first. So let's say sine of 60. So sine is opposite over adjacent. We do need to, well, it would change depending on what we're dealing with. So let's say opposite, so root 3 over hypotenuse, which is 2. So that is my ratio. For cosine of 60, so again, cosine is adjacent over hypotenuse, so 1 over 2. And tan of 60 is opposite over adjacent, or root 3 over 1, or just root 3. Now for an angle of 30, I have to switch what my reference angle is. So I'm going to put a purple theta to represent that. So then sine of 30, opposite was 1, hypotenuse is 2, so 1 over 2. Not theta, cosine, there 30. Cosine of 30 is adjacent over hypotenuse, so adjacent would be root 3 over hypotenuse, which is 2. And then tan 30 is opposite over adjacent, or 1 over root 3. So again, these are the three, or the different primary trig ratios for these special triangles. Right? And again, we know them because they're exact values, and it just happens, it's a unique case with these two triangles. So let's try to use that and use special triangles to find exact values for all sides and angles. So again, the idea is the fact that when we're dealing with certain angles, specifically the 45, 30, or 60, we can use those special triangles to help us determine the missing sides. And we're going to use that by using the idea of similar triangles. So I'm going to draw out just a rough triangle with the 45 degrees. And if I go back and reference my special triangle, this was the 45-degree triangle, had two legs of 1 and a hypotenuse of root 2. So now we mentioned that as long as it's a right angle triangle, and if we have the similar angle like we do here, the 45 and the 45, right, these two are the same, and these two angles are the same, that means this third angle is also going to have to be the same. So therefore we have similar triangles. And that just means that the sides are just going to be factors of each other. So if I can find that factor, and if I look, well, going from 1 to 4 centimeters, that's by a factor of 4, then I have to multiply each other side of my special triangle by 4 to get the new dimensions for this specific example. So 4 times root 2 is 4 root 2. 4 times 1 is 4. So we have an equilateral triangle, or sorry, an isosceles triangle with two angles as 45. And a hypotenuse of 4 times root 2, right? Which is similar to the other triangle, just 4 times bigger. So again, that's how we can use special triangles. Let's look at another example. Angle of 60 and a side of 3 root 3. I need to figure out my missing side lengths. Right? So we do have a special triangle that has an angle of 60. So we have an angle of 60. This is 30. I can go back and look at my primary trig ratios. Right? The opposite, and if I go back, right, the opposite of 60 was root 3. The adjacent to 60, or the angle, was 1. and the hypotenuse was 2. So now that I have my kind of base triangle, I can look to see, okay, by what factor does it increase? Well, going from 3 to root 3, or sorry, from root 3 to 3 root 3, I've multiplied it by 3. So I've increased this side length by a factor of 3. In order for it to work so that all the other angles are the same, right, or all the angles stay the same, I need to increase each other side by a factor of 3 as well. So for the adjacent, 1 times 3 is 3, and for the hypotenuse, 2 times 3 is 6. So that will give me these, or the exact values for the other sides. And finally, the other angle, right, has to be 30 degrees. It's going to be similar to the other one, or have the same angles. We can also use the special triangles or those specific values to help us do some calculations if we're trying to add specific sines or cosines. So sine 45 in this case plus times cosine 45 plus sine 30 times sine 60. So we need to know what these exact values are. So sine of 45 is 1 over root 2. We're going to multiply that by cosine of 45, which is also 1 over root 2. We're then going to add sine of 30, which is 1 over 2. And again, these values I'm getting from all the way back here, right? The primary trig ratio. So sine of 45, or we see up here, is 1 over root 2. Sine of 30 over here, 1/2. Right, so we're getting the exact values from those special triangles, those 3 primary trig ratios that we did earlier. So 1/2 times sine 60. Sine 60 is root 3 over 2. And now I'm going to simplify. So the first one, multiplying 1 times 1 is 1 over root 2 times root 2, which is 2. Or you could say square root of 4, which is 2, right? So again, kind of using our radical properties. And then plus 1 over root 3 times 1, or times 2 over 2. So 1 times root 3 is root 3 over 2 times 2, which is 4. In order to add these, I need to get an equivalent fraction, or sorry, not equivalent fraction, a common denominator. So I'm going to multiply the left fraction by 2, both parts. So it becomes 2 over 4 plus root 3 over 4. So the exact value of that expression would be 2 plus root 3 over 4. And I can't simplify this any further. I can't add a radical and a constant, right? They would have to have the same radical. So it'd have to be 2 root 3 in order for me to add these together. But it's not. Again, this is just the exact value. So this is the exact value. We're not going to go through and punch it into the calculator because it's not going to give us the exact value. It won't be able to calculate it to enough decimal places, or it might, but this is the exact value that we're going to stick with. And put in the special triangles here just so we can, if you're looking back on this page, you can kind of have that reference. Right, so 45 is 1, 1, root 2. And then 60, 30. So the hypotenuse was 2. Across from 60 was root 3. And across from 30 is 1. All right, so just take some getting used to, just some memorization. Right, you might have to write it down a couple times before I kind of get really familiar with remembering some of these special triangles. Now, you can see that when we're dealing with them in terms of determining the exact values, we are going to be dealing with radicals again. So we might have to do something called rationalizing the denominator. And what that means is we just want to get rid of the square root in the denominator just to make it a little bit easier to work with. So the first one, 1 over root 2, in order to get rid of that radical in the denominator, I'm going to multiply everything by the square root of 2. because I know that if I multiply the square root of 2 by the square root of 2, that will cancel out those roots. On the top, 1 times root 2 is root 2, and on the bottom I end up with 2, and that's all we're going to kind of do. Right? We're just getting rid of that radical in the denominator. For b, 3 over 1 plus root 5, right? In these cases, when we have multiple components, we don't want to just multiply it by root 5 because that doesn't help, because then that makes this root 5 and this 5, so I'm still stuck where we kind of started. Right, so what we want to do, if it's something like this where we have two terms in the bottom or multiple terms, right, we want to multiply by kind of the difference of squares, so to speak. Because if I multiply by the difference of squares, right, if we look at the bottom, 1 plus root 5 times 1 minus root 5, right, that's going to cancel out any middle terms, and that's going to kind of make sure that I don't have to worry about having an extra radical in there. Right, so maybe we just want to make a note, difference of squares, which is a plus b times a minus b equals a squared minus b squared. So that will allow me to cancel out any unnecessary terms and remove any rationals or radicals, sorry. So multiplying on the top, the 3 would distribute to both parts, so 3 minus 3 root 5 divided by, this would just be the square root of 1, which is 1, minus root 5 squared, which is 5, which simplifies to 3 minus 3 root 5, all over negative 4. So this is the kind of simplified or the exact value of this expression without any radicals in the denominator. For example, 4, right, we want to go through now and find the exact value of sine squared 30 over 1 minus cosine 30. So sine squared 30, all that really means is just, it's the same thing as just saying that it's squared, but we just kind of put it in between the angle, or kind of in between the trig function and the degree, just to kind of make sure that we're not squaring the angle, so to speak. So we're going to have sine 30 times sine 30, all divided by 1 minus cosine 30. So all I did was kind of rewrite it. Right? I'm going to use the special triangles to replace these ratios or these trig functions. So I'm going to have 1 over 2 times 1 over 2. Right? And again, if it helps, right, we can just kind of draw a quick little triangle, our special triangle. So 45, 45, 1, 1, root 2. And then we have 30, 60, 2, root 3, 1. So sine of 30 is 1/2, so 1/2 times 1/2 over 1 minus cosine 30. So cosine 30 is adjacent over hypotenuse, which is root 3 over 2. I can simplify the top, because 1/2 times 1/2 is 1/4, divided by 1. Divided by 1 minus root 3 over root 2, or sorry, root 3 over 2. I want to add these together. Right, so in order to do that, I am going to make this a fraction. So 1 becomes 2 over 2 minus root 3 over 2. Let's bring this up for more space. So we get 1 over 4. 1 over 4 divided by, I ended up with 2 minus root 3 over 2. because I'm dividing fractions, this becomes 1 over 4 times 2 over 2 minus root 3. I can cancel out here if I want, and cancel out the 4 and the 2. This leaves me with 1, this leaves me with 2. I go through and multiply. On the top, there's 1. On the bottom, distribute the 2 through, so it becomes 4 minus 2 root 3. I want to get rid of that root 3, so what I'm going to do is I'm going to multiply the top by and the bottom by kind of the difference of squares, so to speak, or the same thing, just opposite sign in between. So 4 plus 2 root 3. Which on the top will leave me 4 plus 2 root 3, because it's just times 1. And on the bottom, or the denominator, it will leave me with 4 squared, which is 16, minus 2 squared, which is 4, times root 3, which is, so 4 times 3, which is 12. And then finally, bring it over again, 4 plus 2 root 3 divided by 6 minus 12, which is 4. And then I can simplify because I can take out a factor of 2. Kind of a long process. So 2 times 2 plus root 3 divided by 4. I can cancel out one of those factors. It leaves me with 2 on the bottom. So I get finally 2 plus root 3 over 2. So again, it's a lot, just some simplifying. That's all we're really doing. We're using that kind of rationalizing the denominator step by multiplying both the numerator and the denominator by a value that acts as a difference of squares, and to get to my simplified answer. So it's a lot of dealing with radicals, which we have looked at before, so you might want to review that. But again, similar idea of similar concepts that we've been looking at before, just now applying it to some special triangles.